Hold on a minute. I feel like it's been a long time since we talked about our old friend, Taylor expansion and Taylor series. Did we forget about that stuff? No, we did not forget. Series, Taylor expansion? Oh, that's totally important. That has been so important in so much of what we've done in the past. What about what we're doing now? What about differential equations? Well, let's say we've got just a generic, ordinary differential equation. Maybe it's autonomous, maybe it's separable, but maybe it's not. And if it's not, the techniques that we've learned so far aren't very helpful. So, what if we take this general and generally unsolvable problem and just Taylor expand everything? Can we just do that? Well, you gotta be careful. Taylor expansion does have some technicalities involving things like convergence. Let's ignore that for now. Let's just try. Let's try, assuming that our solution, x of t, can be represented as, let's say a Taylor series about 0. Let's write x of t as the sum, k goes from 0 to infinity, of c sub k times t to the k, where those constants, c sub k, those are just some unknown coefficients. Now, you and I know what they are based on Taylor expansion, but let's just write it as such a series. Well, then what? Well, when we've got a differential equation, we know something about dx dt. So, what is that? How do we compute that? Well, take that series and let's be optimistic. Let's differentiate that series term by term. When we do so, we're going to get the sum, as k goes from 0 to infinity, of c sub k times, what's the derivative of t to the k? Well, that's k times t to the k minus 1. Now, in what we do moving forward, it's going to be a good idea to be somewhat careful at this point with our indices, because if you think about it, when I take the derivative of this series, the constant term goes to 0. Now, you can see that if I plug in k equals 0, technically it kills off c naught, but let's be careful and use the following convention. When we compute dx dt, let's set that sum going from k equals 1 to infinity. And then we've got k times c k times t to the k minus 1. That's the way that we're going to present a derivative. Okay, so fine, we've got this convention. What do we do now? What do we do with this? I have a series for x. I have a series for dx dt. I have a differential equation that relates dx dt to some function of x and perhaps t. What do we do? Well, I'm not going to say quite yet. What I am going to say is that in order to get at the solution, we're going to need to work with these series. We're going to need to use the following principle that is important enough to call out here and now. If you have two series that give you the same function, then this is so if and only if all of their coefficients match. What do I mean by that? Let's say I've got a function that is given by the series sum k goes from 0 to infinity of a sub k t to the k, where the a sub k are some constants. And then I've got another function that is given by another series, the sum k goes from 0 to infinity of b sub k t to the k. I'm using the same index k for both series, and let's say that we know that these two series give you the same function. If that's so, then all of the coefficients have to match. That is, a sub k has to be equal to b sub k for each and every single k. And this is if and only if. That means if you have two series and the coefficients are all the same, then they're giving you the same function. This is just a general principle to help us set up a series-based solution to differential equations. And now we're set. The pieces are in place for what is going to come next, which is some examples of series-based methods for differential equations. We're going to start off simple with things that we already know and then move on to more difficult examples.